Okay, so can you see my screen?
Yeah, we can see it clearly.
Okay, thank you very much to you and to organizer for giving me this opportunity to talk about some of the things I work on. So I'll be talking about cross-sections computations, uh, examples of computations based on some of the data we did collect and some of the data that we wish to collect. So I will explain how one goes from yield to the cross-section, and then I will show two examples, one a simple case with the monoenergetic beams, and another more complex case where you have multi-energetic or white beam. So let me get straight into it. So normally the cross-section is not directly measurable quantity, so what you need to measure is yield. Now, typically, cross-section connection to the yield comes together with the integral, which is then combining cross-section with the flux. Here, I'm focusing on the cross-section as total cross-section, although in principle, if you just differentiate this by angle or by energy, you can get then differential cross-sections. But for sake of simplicity, here I will just focus on the total energy-dependent cross-section. Now, the question becomes, depending on my incoming particle, my incoming beam, how can I work with this equation? Obviously, on the left side, I have the yield, which comes, or which is part of the measurements. But then on the right side, depending on what kind of beam I have, I can change things. So then this brings us to a simple case. If this flux, this phi can be a delta function if my incoming beam is monoenergetic or very nearly monoenergetic, then the integral disappears, and what I have is just a simple linear equation. So that is the case if you work, for example, with protons or electrons or other charged particles, where you can then essentially eliminate this integral. Obviously, when you're measuring things, even to get to the yield, it's not direct. You still need some reformulation. But if you take all the quantities that you have, take into account how long it takes, the time to take the experiment, what type of nuclear you have, what is its charge, how long you have been bombarding it, how much material you were bombarding, as well as what is the overall incoming flux number of particles, and then rework it with some algebra, you get on the left side then the cross-section, which is then obviously dependent only on the energy of the incoming particle. The thing that is the most difficult to quantify, to measure in this case, is then peak area. So what you have here is then some sort of spectrum, which you then have to analyze, associate that particular peak, eliminate background, and then associate the area of that peak with the cross-section. But at least at this level, you're just dealing with algebraic equations. There is no longer the integral equation, which we'll meet again later. So in case of protons, this is what we were aiming at first time we did something like this. What you can do is what is known as stacked foil technique. The advantage of this technique is that you can at once measure several energies rather than measuring them one at a time, by combining this property of heavy charged particles that you see in the bottom left angle, which is known as the Bragg peak, that in the beginning of the Bragg peak, actually before the Bragg peak on the left side, the energy loss is constant or very nearly constant. So if you put a degrader in between your samples, then you know by the thickness of this degrader how much energy has been lost. And then you can do several, depending on your primary beam energy, up to 10 different foils simultaneously. However, since you don't know a priori how much you're actually losing energy in the degrader, you also have to have a monitoring foil, which will then tell you how much energy you're actually losing at each step. In this way, in this setup, you get a convenient way of measuring cross-section in this charged particle case. typically, to get then a good reading of the outcome of the reaction, you then need some detector which will be able to measure the spectrum of the outgoing particles. And most commonly, these are either germaniums in recent times, in certain cases also lanthanum bromide detectors. But in the past, this has been done with sodium iodines. And even though their energy and their energy resolution is not the best, if you pick your reactions carefully and you pick a situation where the peak is clearly visible, in this case, you can think of cesium-137, which has effectively only one peak, and it's then easy, even with the sodium iodine, with such a poor resolution detector to work. So the message here is that depending on what kind of reaction, what kind of situation you're working with, different tools can give you different options, and it's not always necessary to have a very complex multi-detector setup. That even setups with relatively low resolutions can work rather well. From these detectors, from their peak and peak areas that you determine, then you get to your yield. And by the equation that I showed earlier, then from the yield, you can get to the cross sections. So what we did here in the Ankara area, there's a proton accelerator center in Sarayköy operated by TÜBİTAK. And we wanted to see if we can measure the cross sections as induced on praseodymium 141. Why praseodymium? So as I said, you have to pick your reactions carefully because as you see, a proton reaction induces many different reactions. If you go from praseodymium, if you have, let's say, 30 MeV, you can excite all of these potential reactions. Now, you won't see necessarily all of them, but all of them are possible. In fact, there are a few which are possible. I shortened this picture a little bit. There are a few which are possible, which are actually not listed here. And then one of them we actually even observed. All right, so this is how it looked like on the left bottom. You can see then the target and the target holder. In the center, you have the aluminum foil, which serves as the holder. And behind it is the actual, did I go to, no, okay. Is the actual praseodymium. On the right side, then what you can see is then the actual spectrum observed of this particular foil. So in this case, we did the simple test, just a single foil, and we were able to identify 3 reactions. The first one is 3 neutron separation. The second one is a single proton and a 2 neutron separation. And the last one, this is the one that I was mentioning, is actually not on the graph previously shown. That one is an alpha particle separation, which went 1 proton down compared to the figures previously shown. So you can now take any of these peaks and do the data analysis on them. You also have to then analyze in parallel the monitoring foils and know what is the flux and the energy which was actually impacting the foil. For example, in this case, the nominal energy coming from the accelerator was 30 MeV, but once controlled by the monitoring foil, it actually turned out to be 27.5. From there, we were able to calculate the cross-section. Unfortunately, due to the richness of the spectrum that you see here, as well as the existence of a large number of interfering reactions, the determination wasn't very accurate. So somewhere between 250 and 500 millibar, but it was in the right area. So what we learned from this experiment is that our single detector setup, which we were using for this particular experiment, was insufficient. So what we need in this case to do is find a way to resolve or separate these peaks such that you can sort of simplify, at least in one case, your spectrum. From the resolution, I hope you can see that this is a germanium detector, which had a fairly good resolution, but as I said, it was working alone, and it was working without any Compton suppression. So since this time, what we are trying to do is upgrade our detector spectrum to include Compton suppression. as well as to work in double detector setup where one of the detectors would be in coincidence, one of the germaniums would be in coincidence with the other, such that you can then simplify the spectrum by gating on one of the detectors. For example, if you look at the very first peak around 100 keV, if you gate on that peak, all the non-yellow peaks would disappear because they are not in coincidence with it. So that would simplify the spectrum and enable a better determination of the cross-section. Nevertheless, we were quite happy with this first experiment that we performed. We identified 3 different reactions. We were able to calculate one of the cross-sections for the first of them, and this was a good first step. Now let me go back a little bit and talk a little bit about theory. So in theory, when looking at proton reactions, you can have either in-last scattering, where the proton is not absorbed, only a gamma is emitted, or you can have an absorption. Both of these first 2 reactions are importantly have no threshold. In the very first one that I showed, I also included in the integral the threshold, because many reactions, for example, the next one, the one with the proton and the neutron, has a threshold, and of course, if you have more than one proton, that threshold increases further and further. So with 2 and 3 and more neutrons emitted, there's a bigger threshold. Obviously, the same happens when you're trying to kick out a proton. Here, obviously, X goes only from 2. The first one shows the X1 case. And then, of course, then you have more complex cases where you're ejecting both proton and a neutron. This can be, for example, an alpha particle, which is a relatively easy low threshold reaction. But if you're kicking out 3 protons and 2 neutrons, that becomes a more becomes a higher threshold. The arrangement was as this, as I showed earlier. You have your monitor foils, your target foils, and the beam comes from right and goes to the from left and goes to the right. This is the site. This is the proton accelerator in, as I said, in Sarayko in Ankara. This is their research Arge room. The beam is indicated with the right arrow coming from the wall through the selector magnet and goes into the scattering chamber, which is a vacuum chamber where the source, the target is placed. This is the actual then position of the target. You saw only this holder earlier, but this is how the whole chamber looks like. Obviously, everything is happening in vacuum, and the other holders are meant for beam monitoring and beam size monitoring. The target, in case of protons, also has to be thin. So we use the sputtering method to coat aluminum backing. Here, we tested it first with glass just to see what kind of uniformity we get. This is done here at Tarla. There's a magnetron spattering device, and we were able to achieve a few micrometers thick targets, which is, as I said, quite important for these proton charged particle experiments, because if you have a thick target, you could work with that as well, obviously. But then you have to go back to that yield formula and keep that integral, because your beam energy would be changing through your sample, and it would no longer be a nice sharp constant like it is at the beginning, at the entry. Now, to design the experiment to also to see what kind of reactions are suitable for monitoring, we looked into what is possible. Typical monitoring reactions include aluminum, titanium, nickel, and copper. In our case, due to the energy consideration, copper was the most appropriate. The copper is chosen because its cross-section is very, very well measured, and it's, as you can see here, there are dozens, in some cases over 20 different measurements of the same reaction, and they are all combined by the EIA into a single output, a single very highly reliable cross-section, which then introduces little to no error into your own cross-section measurement. Now, to design the experiment, obviously, we need to consider how thick the targets can be, how many targets we can do. And for that, we have to go to simulations to see what is appropriate. So if you start with the spectrum of the incoming protons, which you see here on the left side as the first right curve, that enters your first monitor. And here, as I said, 30 was assumed, and we determined it as 27.5. Then, as you go along, you both lose energy, so you get 28, 26, and so forth. But if your eyes are very good, you can also notice that the beam spread is also increasing. So that assumption from the beginning that the flux is constant, or let's say delta-like or nearly delta-like, slowly degrades. And at some point you have to say, okay, this is as good as we can tolerate. Making more degraders and more foils spoils this monochromatic assumption in our cross-section that we make earlier, and we have to stop it in this case. Unfortunately, there's a detail connected to praseodymium that it's not part of the many databases. So you actually cannot simulate praseodymium, but you can simulate the neighboring cerium, which has a similar density. And here, in this case, density is the only thing that is relevant. So you can simulate that. That gave us a design of the experiment for 3 foils. As I said, we did the test for a single foil that was successful. We designed then the next full experiment with 3 foils. And hopefully, once our detector setup is ready, we'll be able to do the full 3-foil experiment soon in the future. I'll skip this part. This is what I was mentioning earlier in red, how we determine the energy from the Koppel monitoring foils. This is just repeating. Okay, so that was the simple case. That was the case where your incoming beam is monochromatic. So let me show again the same slide. Only this time, let's focus on another case which we hope to do in the future. We did some, over the course of many years, we learned sort of the hard way how this formula can be quite challenging. So if this phi is no longer delta function and the integral remains, if you have a multi-energetic white type spectrum, then this procedure of extraction cross-section becomes much more complicated. This is in fact the case if you're working with neutral particles. What I'm showing here is the spectrum of photons as they come out from a foil which is being bombarded by charged particles, most commonly electrons. This is known as the Bremsstrahlung spectrum, and here the energy the maximum energy of the photon corresponds to the incoming charged particle energy. So you get all energy losses, all possible energies from that maximum energy represented by your incoming particle nearly down to the 0. And then if you change that from, let's say, 18 to 20 MeV, then you can get a different type of circuit. But here the point is, it is not a nice monochromatic spectrum. It is a white spectrum. So what you can do with this Bremsstrahlung photons, these are known as photonuclear reactions. Here, similar to the protons, you have different type of reactions. In this case, the incoming particle is the photon, not the proton. So you can kick out a single or multiple neutrons, single or multiple protons. Obviously, you can have also inelastic scattering, gamma-gamma prime reactions, or you can have fragmentation where you split the nucleus in a fission-like or induced fission-like reaction. When you look at the cross-section now, your entire cross-section is actually overlapping with your Bremsstrahlung spectrum, and in order to work with it, you need a different method than just a simple algebraic equation. So what you need is then a type of unfolding. So you need to convert your integral equation to set of linear equations. So if you took theory again, this type of integral equation that you see is known as Volterra integral equation of the first kind. If you want to do a numerical solution, which is obviously something that you need to do with the experiments, is the method of quadratures. So this method constructs an approximate solution based on the replacement of this integral with the sums. You see the formula written out at the bottom. So once you do that, you get a system of equations. Now, you have seen how difficult just one experiment in the proton case was to extract all the peaks, all the areas. Now, in this case, you can have 10 or 20 or even 30 energy points for which you're doing your photon-induced reactions. And now you have for each of them to do the peak analysis, for each of them to do the yield calculation. And then once you're ready with the yield calculation, you can put that yield into this equation. And from solving this now system of linear equations, you can hope to extract the cross-section, which is far on the right side. In all cases, obviously, you need to know the flux, the Bremsstrahlung flux. And this is what was what is sort of difficult when you look at the solutions, that in each of these, both the solution itself as well as the error of the solution, you have the Bremsstrahlung flux appearing in every case. So historically, this has been a real challenge. So this unfolding equation, how to obtain, how to measure, how to quantify this Bremsstrahlung flux has been a challenge. Often what was used was very approximate analytic solutions to the Bremsstrahlung spectrum. And then that led to a case which was measured recently, I think in 18 or 19 by the new Subaru, which then gives a completely different, this is a different method, not with the Bremsstrahlung. All the other older results from 59, 62, and 74 are all Bremsstrahlung, but you can see the squares have this sort of oscillating pattern as well as exploding errors as you go higher and higher in energy, because each of the errors that you incur at energies of, let's say, 10, 11, 12 MeV propagates to your 20 MeV error, because you have actually taken a solution of an integral equation going from 10 to 20. This difficulty is something that we hope to, or that is more easily solvable nowadays, because we can do a better calculation of the spectra. The spectra that I showed you earlier comes from a Monte Carlo simulation. Here, instead of making an analytic approximation to the spectrum, we can actually do a simulation and take into account geometry, and not just geometry of the targets, but geometry of even the surrounding materials, and have a much more accurate spectrum, which has then, which needs only two characterization. It needs the characterization of the endpoint energy. That means you need to measure your incoming electron beam very accurately, and the overall absolute total flux calibration. So that would be, on this case, on the Y scale. So here, this calculation is per incident particle, per incoming electron. You need to know how many you have. Unfortunately, that accelerator doesn't typically provide this in a very accurate fashion, but there are ways to measure this fairly accurately. Beyond that, the shape of the Bremsstrahlung spectrum is then provided by the Monte Carlo simulations. So the beginning of this story with the photons and photon nuclear reactions with us started in my previous workplace. As I mentioned, currently I'm working at Tarla in Ankara, which is an electron accelerator center. But the very first measurements I have done with colleagues in Antalya, and this is now an example of spectrum. As I said here, we stopped only at 1, and from 1 you cannot extract the cross-section, because at best what you can obtain is yield. But even just analyzing this one spectrum provides a lot of experience and know-how for hopefully what will be the future here at Parla. To illustrate how bad the situation is in this particular case in the results of the photonuclear cross sections, let me show you two very standard nuclei, iron, and next one will be zinc. And you can see that since the 70s or the end of 70s, they have not been remeasured, and the measurements are not in agreement with each other. And you would think, okay, this is not an exotic nucleus, this is not dysprosium or erbium or some rare earth. This is simple iron. You should be able to have a reliable photonuclear cross section and a single neutron separation. For proton, there's even less data. And that's even, let's say, a good situation. Let's say there's some data. If you go to zinc, there is no data. And again, once again, zinc is not an exotic nucleus. You don't need, and they're both metallic, very easy targets to work with. So the challenge isn't the targets or the materials. The challenge is the data analysis and how you extract the cross-section. So let me introduce Parla briefly. So here in Ankara, we are building superconducting linear accelerator. It's consisting actually of two trio modules, LINAC 1 and LINAC 2, labeled here in pink. The injector for the first accelerator starts with an electron gun, which goes up to about 250 keV. After the first linear accelerator, first cryo module, we have the 20 MeV, and finally, after the second one, we would have 40 MeV. So the accelerator would be able to produce anything between 0 and 40. In practice, it is more like 5 and 38, but to first approximation, that is that. On the corner of the facility is where we are planning to do our nuclear experiments. That's the nuclear experimental station, which we refer to also as the Bremsstrahlung, because Bremsstrahlung is the primary beam there. So on the peak area, what we have are the electrons, but once we pass from that area to the nuclear experimental station, we would go from electrons to photons, and then photons will be in the nuclear experimental station. To zoom in a little bit, past the second linear accelerator, we have a set of magnets which steers the beam, the electron beam, onto this conversion targets. To avoid confusion with the experimental targets, we typically refer to these as converters. So their job is to, they are also foil-like and look like targets, but their job is to convert electrons to photons. And then all the electrons which are then not converted are then bent away by this steering magnet, by the selecting magnet, onto the beam dump that stays in the accelerator hole, and through the wall, through the collimator inside the wall, we enter the Bremsstrahlung room with the photon beam. This is how it looks in a bit more detail. So the red line here represents the electrons, and then once you reach this dipole magnet, which is shown in green, beyond that, you pass through the wall with just photons, and then you collimate those photons. And on the Bremsstrahlung station, you have your experimental target, which would have detectors around it. Before that, obviously, as I mentioned earlier, you need to quantify your photon beam by knowing its maximum energy. And for that, we have this photon diagnostic station. This is how the targets look like. They are very thin metallic foils. In principle, you can use almost anything to, every material creates Bremsstrahlung. However, from the engineering point of view, the easiest ones to work with and the easiest ones to manage heat are the metallic ones. For various considerations, because different materials have different separation energies, separating a neutron or a proton, what you want at least one is a material which has very high neutron or proton separation energy, and aluminum is that material. So for the highest energies, we would use aluminum either thin at 20 micrometers or a little bit thicker at 40 micrometers. Once you go to lower energies, as I remember, as I mentioned earlier, Tarla can go down to 5 MeV or even lower. So in that case, to maximize your photon production, you would use either copper, tungsten, or gold, depending on specific needs of a specific experiment. Again, to understand what we expect, we did all sorts of Monte Carlo simulation here, what kind of spectra we would expect, what kind of fluxes we would expect, this type of, as well as what kind of heat deposition, because heat deposition is the limiting factor for the foil thickness, for the converter foil thickness. So that's the converter, that's the creation of the Bremsstrahlung side. So then on the detector side, we are intending to use 4 germanium type detectors. 2 would be single crystals and 2 would be clovers. Clover is a detector type where you have the germanium crystal, but it has been segmented, meaning that effectively you have 4 crystals which are now so close to each other that they can be considered as a single detector. Obviously, for all of them, we have the active quantum suppression. So that's coming in the form of the BGO detectors. And then they will be placed 45 degrees with respect to the beam, or minus 45 degrees, depending on how you look at it, and 90 degrees to each other. The placement of the germaniums in the backward angles is needed because they cannot tolerate very high count rates. So the beam itself has a huge number of photons, 10 to 11, 10 to 12 or so, whereas a single germanium crystal can handle at most 10,000 or so. You know, that's already high. However, what you still want is to get as much data as possible. For that purpose, we will use lanthanum bromide detectors will be placed at 90 degrees toward, with respect to the beam and 90 degrees with respect to each other, because they can handle as much as 1 million counts per second, 1 million interactions per second. So this gives you then the high count rate, as well as the very high resolution coming from the germanium detectors. Depending on needs of experiment, these can be performed either in coincidence or out of coincidence. Obviously, BGO is always a coincidence with its own germanium, but between germaniums, between the lanthanum bromides, you can make various types of combinations of various types of coincidences. With that, I would like to stop and ask, are there any questions? I'm well in time, so there's plenty of time for questions, and so feel free to ask. Thank you very much for your attention.
Thanks for that nice talk. Any questions? Hocam buradan. Okay, we have one question.
Hello, Harris. How are you? This is Orkun.
Good.
Yeah. Just one quick question. You know, the integral equation you've shown.
Yes.
You know, we basically solve for the transfer function, right? It's can it be considered sort of a Green's function representing the transfer of the
in theory, yes, if you have enough data points, if you're, for example, simulating your spectra and you're doing simulated experiments, yes. But in case of the detector data, you cannot have so many data points. So then it's better to go numerical, to go with the sum rather than an integral. But if you're talking about simulated experiments, then yes.
Yes. So in other words, we are considering the entire detector system as a linear system, right?
Yes, in
Yes.
this, yes, it has to be considered as linear because it has to be considered as discrete.
Yeah.
You
So in
break it
other
up
words,
to
there is
discrete.
no cross correlation or effect, of different channels on different frequencies on other frequencies.
No,
So it's
no.
linear system of okay. Okay.
Yes,
Thank
yes.
you.
Thank you. If there are then no more questions, I have one more comment. So currently, Tarla is completed its 20 MeV part of the accelerator, and we hope to complete the 40 MeV in the next 9 months to a year. So in about, let's say, 6 to 9 months, we will be looking for quite a few students for experiments. So if there are those who are interested, please keep an eye on our website. We also will have projects, and we have written proposals which will hopefully be approved by TÜBİTAK. Once they are there, we will also have scholarships for both master and PhD students. If there are questions, also somebody wishes to ask in Turkish, that's also fine. That you can also ask in Turkish. Okay, I guess there aren't any questions.
Yeah. Okay, thank you very much again.
Yeah, thank you.